Welcome to This Explainer. Today, we're taking the abstract, sometimes intimidating world of algebra and translating it right into our tangible, everyday reality. We're going to unpack Chapter 2 of the Manjari mathematical text. You know, if you've ever stared at a mathematical equation and thought, come on, when am I actually ever going to use this? Well, you are definitely in the right place. We're going to reveal how the underlying math of the universe is actually hiding in plain sight, right in the most ordinary moments of our daily lives. So let's kick things off with a slightly weird question that's actually going to unlock our entire journey today. What could a standard auto rickshaw fare possibly have in common with a small plant growing in your garden? I mean, on the surface, absolutely nothing, right? One is basic commerce and the other is biology. But if we look through the lens of mathematics, they are practically identical twins. Let's look at the numbers to see exactly why. If you actually look at the data, a rickshaw fare builds an incredibly strict mathematical pattern. Chapter 2 of the Manjari gives us this perfect example. Imagine you hop in, and the fare starts at 25 rupees for the first 2 kilometers. Okay, pretty standard. But after that base distance, the meter starts ticking. For every single extra kilometer you travel, the fare increases by exactly 15 rupees. So 3 kilometers is 40 rupees, 4 is 55, and so on. It jumps by exactly 15 every single time. I want you to keep that steady 15 rupee heartbeat in mind. Now, we see the exact same thing in nature. If we track a plant that starts out at a height of 1.75 feet and it grows exactly half a foot every single month, we're watching another highly predictable sequence unfold. Month 1, it's 2.25 feet. Month 2, 2.75 feet. Just like that rickshaw fare, we are seeing a quantity increase by a fixed amount over equal intervals of time. So what's the big secret here? Well, both of these totally different scenarios share a hidden fundamental heartbeat, a constant difference. Whether we're tracking distance traveled or months passed, the resulting value grows by a fixed, unchanging amount. In math, when a quantity increases by a constant amount over equal intervals, we call that linear growth. And, if it were decreasing, like your prepaid phone balance draining by 15 rupees a day, we'd call it linear decay. But how do we formally describe this? That brings us right to what mathematicians call a linear polynomial. It's just the formal vocabulary for these constant everyday patterns. A polynomial is simply an algebraic expression that uses a variable and its powers. But that word linear is the absolute key here. It means the highest power or degree of that variable is simply 1. So you aren't going to see an x squared or a y cubed, just a plain, simple variable mapping out a completely steady rate of change. Honestly, the best way to visualize a linear expression is like a highly predictable input-output machine. A factory line, basically. Say our machine is programmed with the linear polynomial y equals 2x plus 3. If we drop the number 4 into the x slot, the machine takes it, multiplies it by 2, adds 3, and spits out an 11 as our y. Every single time you drop a 4 in, you will get an 11 out. It is a perfect, unshakable relationship. Because of this consistency, we can take our rickshaw fare and directly translate all that real-world messiness into a tiny, concise equation, y equals 15x minus 5. Because we paid 25 rupees up front for those first 2 kilometers, and then 15 for each one after, the whole real-world scenario simplifies perfectly into just these 5 little characters. It's kind of amazing how the messy real world is suddenly captured mathematically. It really proves that algebra is just a translation tool. The master blueprint for all of this is y equals ax plus b. It gives us a beautifully clean way to write down the rate of change mixed with the starting point. The x and y are our input and output. That a is our constant difference, it's the slope, or basically how fast that rickshaw meter is taken up, and the b is our y-intercept, which just adjusts for whatever our starting condition was. Literally every linear pattern you will ever encounter fits right into this elegant little box. All right, so we have the vocabulary and we have the blueprint. But here's the fun part. What happens when we take these abstract letters and numbers and actually try to draw a picture of them? Because humans are highly visual creatures, right? Reading y equals ax plus b is one thing, but how do we actually see the math? How do we draw a picture of a rickshaw fare or a growing plant? It's surprisingly simple. You just take an equation, let's use y equals 2x plus 1, and find a couple of input-output points. If our input x is 0, our output y is 1, so we just put a dot at the coordinate 0, 1. If our input x is 3, our output y is 7, so we plot another dot at 3, 7. Then grab a ruler, connect those 2 dots, and extend the line out in both directions. You've just created a visual map of the pattern. And here is the absolute most beautiful part of all this. Every single linear polynomial Then al-Biruni used coordinates for mapping, paving the way for the Persian polymath Omar Khayyam. And what's just mind-blowing here is that Khayyam's groundbreaking ability to literally draw the solutions to algebra problems, it relied entirely on those earlier Indian number systems. Khayyam was a total expert in the Indian decimal system. By taking algebraic equations and interpreting them as physical coordinates on a plane, he was the very first person to solve them using geometry. He essentially proved that algebra and geometry are just two different languages describing the exact same truth. Right, and let's be absolutely clear on this. Without Brahmagupta stepping in and formalizing zero and mapping out positive fortunes versus negative debts, the four-quadrant graph we literally just used to draw straight lines simply wouldn't exist. He took the ancient philosophical concept of shunyata, or emptiness, and turned it into the mathematical zero. And then he realized, hey, if you subtract a larger number from a smaller one, you fall below zero into what he called debts, which we now call negative numbers. The entire left and bottom sections of our modern coordinate plane are built entirely on Brahmagupta's genius. So as we wrap up this explainer today, I want to leave you with a bit of a challenge. Look around your room right now with a mathematical lens. Try to find the hidden straight lines in your own life. We've seen how a bumpy rickshaw ride is actually a perfect algebraic equation in motion, and how an ancient philosopher's concept of nothingness allows us to draw that motion on a grid. Math isn't just stuck in textbooks, it's the invisible scaffolding of our entire reality. So what linear pattern is playing out in your life right now? Is it your phone battery draining? The cost of your monthly streaming subscriptions? Find it, plot it, and you'll start to see the straight lines connecting absolutely everything. Thanks for joining me, and keep exploring.